Swayam Prabha. Digital India. Educated India.
Welcome back. So this was the last slide where we were talking about the phenomena of liquefaction which was observed in 2001 Bhuj earthquake. And as I told that in most of the region which was we can say the low-lying regions with near surface saturated soil liquefied during 2001 Bhuj earthquake ground shaking. This ground shaking was quite intense, and as I told that the people, local people, they believe that this is the time when there is a revival of or rejuvenation of the ancient river which used to debouch in this region, and the Saraswati. So this was the epicentral area, and I'll show a couple of slides what we recorded after the earthquake, the ground deformation in this region, and also in this lecture I will show the liquefaction features which we observed and noticed from the Great Run of Kutch. So mostly the hard rock area of course also experienced severe shaking because the epicenter was not so far from this region. This whole area, most of the cities and the towns were devastated. So this was the data which was been captured after 2001 Bhuj earthquake. This shows in particular the region south of the main rocky land, that is the mainland Kutch, and this region is your Bunny Plains, which shows the liquefaction in Run and Bunny Plains. These are the pictures from New Madrid, the earthquakes which were been triggered in 1811 and 1812 in US. And this is the picture, aerial photograph, which we took after the 2001 Bhuj earthquake in Gandhinagar area. So this is the coastal region, and most of the areas, and this what you see is all are the tidal channels, and the square white squares which you see is the salt agricultural field. So this is salt pans which people very commonly do for the producing the salt. So this all black patches which you see here is the sand boils which developed at the time of during the ground shaking, and the whitest patch are from the photograph which was taken after the 1811. Now these two earthquakes have been compared because till date we consider that the Kutch region is the region of stable continental region where which is sitting away from the most seismically active zone like Himalayas. These were the sand blows. As I was talking on that day, that this typically resembles a volcanic cone, and then along with that we also see the formation of longitudinal fissures, and these fissures were also instrumental in pouring out the liquefiable sand as well as water which was present close to the surface. You can see the wide fractures or the fissures which were been formed, they were full of water. So the terrain of Great Run of Kutch is very hostile and very flat region. Mostly you don't see anything in this region except the small bushes which are growing, otherwise it is completely flat terrain comprised of very fine tidal deposits. Now, this road is of course recently constructed mainly for the movement of BSF Jawans, and this is the pictures from Great Run of Kutch. And in some locations where we don't have road, we need to move on the marshy land. So this picture, if you see, I put myself as in scale to show the dimension of the sand blow. So this is the sand blow which was before this before excavation, we were not aware whether this is a sand blow or not. But as I was showing one picture that from Gandhinam and New Madrid, where we were able to see some white patches or the white dots. So this is very much similar to that. So there is a difference between the color of this surface and the sand which is sitting here. So that what prompted us that most likely this is a sand blow, and the recent event which was triggered was 2001. So this field we did in 2005 and 6, where we encountered this features. So this is close to the Alaband epicentral area. So finally, what we decided that if really this is in sand blow, then we should see some liquefaction features. Hence, we started digging at some locations and of the same sand blow, and what we found was a beautiful contact between the surface or the topsoil or the sediment succession and the alien sand which came from below. So you can see the dimension is quite wide, and that resulted into the pouring out of this whole sand boil or the sand blow which we have seen. It's more than 2 meters in diameter. So this was not the only one conduit or the dike through which the sand was poured on the surface because of the increase in pore water pressure. So you please remember what we discussed in the previous lecture, that the ideal conditions for triggering the liquefaction is the cohesive-less sediments. One. So what we decided that to dig, and this was the exciting moment for us to see the alien sand having contact with the near surface succession. So this sand is definitely which came up from subsurface. So if we just put the sketch here of this section, what we see is that we have the horizontally laminated succession, which is definitely in tidal succession we have, and then the sand which is sitting here is something like that. Okay, so this sand is probably coming from, or not probably, we can say that this is coming from some subsurface, the sand sitting here, and this whole area is your tidal sediments. So this was one important finding which we saw, and this is good for the understanding that what exactly happened during the liquefaction, apart from what we used to see in the textbook. So what we need to have the ideal conditions for this is, one is we need to have the cohesive less sediments, and B, water saturated. So this is two very important point which we need to keep in mind. And of course, another important point which I will come later is the overburden. This is again an important point. That is the overburden, which what I am talking about is the suppose we have the non-liquefiable layer, okay, either it is clay and then we have a liquefiable layer here, and maybe it is also sitting on the top of the unliquefied layer. So if this is a section we have and this portion is water saturated, then chances increases of having the liquefaction. But at the same time, if the thickness of this is large, okay, greater than the, suppose we put this as an H1 and this is H2, so if the thickness of H1 is greater than H2, then in that case the liquefaction chances become little meager. So if H1 thickness is greater than H2, because it will not be able to break this unit in that case. So this we will talk later. So let's see a few more examples from the Great Run of Kutch, how it looks like. So this is a section, so this portion which you see is the plan view, and the horizontally, and this is the vertical section. So you see a big from this is the conduit which is coming up and then getting up vertically here. So very huge sand blow which was been observed here, and this is the contact between the laminated sequence here which I was showing in the previous one, and the sand which is coming. It's a pure sand which has been poured out on the surface. Definitely this also indicates that this is all riverine deposit or the floodplain deposit which was deposited by then existing mighty rivers. There's another picture of the same trench where you can see the contact, the horizontal on the flat surface and then vertical surface over here. So very thick sand which was been poured. So what we found was, so this was not only the one sand blow, we were having multiple sand blows which were been observed in this particular region. So as I told that if you have an ideal condition, then you can have the liquefaction even at the magnitude of 5.5, but the shape or the size of the sand blows itself indicate that the magnitude was much higher than 5.5. So there is another relationship and the studies which have been done which also tells about that what will be the size or the dimension of the liquefaction structures or the features depending on the magnitude. That is another point which is important. Now before I go to the further detail, one important point which I would like to mention here, that this area, because it is absolutely no habitation, no one stays here because of its hostile condition and the completely flat area, no damage or there was no hazard because of the liquefaction here. But if similar terrain is there where we have thick population or the area is thickly populated, then this phenomena or the process is a matter of worry. So what we did was another a typical exercise. We collected the samples from the sand blows, and we are planning to date the samples which will tell us that when exactly this liquefaction took place, and of course the date will be close to 2001. Another feature which we found was again a very interesting one, that we saw a sort of a mole track, and then initially we thought that this is an insect burrow or some animal which traveled through this might have created these burrows and all that. But this was we were able to see such fine cracks and then raised up land here or the material along this line for kilometers. Then we decided why not to see the section, and then what we did was that we opened up a very small trench which clearly indicated that this is a feature related to the sand dikes. So the previous one which I was showing was sand blow. The feature which we saw was circular, and in some areas I was showing the photographs which was been taken something like this, and then at the center we were having the cone, the typical cone structure. So this is another, so sand blows, but these are the dikes actually. So an interesting thing which we found was that these dikes showed us fragments which were been broken from this soil. So close up of that, if you see here, what we see is this is the contact between the laminated sequence here, pure sand coming here, and then in between this, within the conduit, we have some broken fragment. Close up of that, if you see, is this one here. So these are some broken fragments of the soil, the capping soil. So these are all disoriented. I'm talking disoriented in the sense, if you see here, you see the laminations which are seen almost horizontal over here. So these are all disoriented fragments, broken fragments, which were been carried within the dike when there was a sand movement. So this is a typical example to prove, also to show that this material, that is the sand, it came up from the surface or from the unit which was sitting far below from the surface, and it broke the overlying units. This is another example from the same trench which clearly shows the disoriented fragments. Now the factors which I was talking, apart from the strong ground shaking. So one, you have the ground shaking because of the earthquake. Second is the water saturated sediments, and water saturated sediments should be near surface. But of course we also talked in one of the slide in the previous lecture that liquefaction can also take place in the deeper part, but that may not reach right up to the surface, so it will die out in form of sills. And then we should have cohesionless or cohesiveless sediments, which are loose granular sediments. So if you see, basically what happens is, so this is the photograph which was taken after the 1906 San Francisco earthquake, and if you watch the movie again, you will be able to see that house which has been shown here in the sketch. So basically what these are the three factors which we have listed here are important. So you need to have a very strong ground shaking. This is an ideal condition for the liquefaction, loose granular sediments and water saturated sediments. So as soon as the pore water pressure increases, it will result into the loss of shear strength of the cohesiveless sediments, which will result into the phenomena of liquefaction. Thank you so much.